Okay, so what we'll do now is example 315.1, in which I've modified things a little bit. High is black, low is red, and instead of meet and pass, I have call and fold. But those are the only changes from example 315.1. It's basically a simple card game. There are two players. They both put in $1 to begin with. Player 1 is dealt a card and she privately observes it. So she knows what card she has, but player 2 doesn't know. The card could be either a spade, clubs, hearts, or diamonds. If it's one of the black suits, so spades or clubs, then player 1 wins if there's a show, and red loses. After seeing her card, player 1 can either choose to see or to raise. If player 1 raises, then player 1 puts in another dollar, and player 2 has a chance of either folding, giving up the dollar that she had put in initially, or calling that raise by putting in another dollar and demanding to see player 1's card. These are the payoffs, and this is the structure of the game. Chance plays first with a 50% chance it's red, and with a 50% chance the card is black, which is why I chose black and red instead of, this should be black here, and this should be red. Okay. That's why I kind of switched from high and low to black and red, because in a standard 52 deck, 52 cards deck, there's 26 black cards and 26 red cards. High and low makes less sense because there's a total of 13 cards per suit, and so no matter where you draw the line, because you have an odd number of cards, a 50-50 split makes no sense. Anyway, maybe the authors of the book weren't dealing with a standard 52 card deck. Alright, chance moves first. The card dealt to player 1 is black with a 50% chance, red with a 50% chance. Player 1 in either case has the opportunity to either see or to raise. Here, if player 1 chooses to see, player 1 gets 1 because she has a black card and black cards win. She gets to keep the dollar that player 2 put on the table, and player 2 loses her dollar. Here, if player 1 chooses to see, player 1 loses that dollar and player 2 gains that dollar. Right? Because they both put in a dollar. So player 2 here would gain player 1's dollar. On the other hand, player 1 also in either case has the opportunity to raise, to demand that if player 2 wants to see the card that player 1 is holding, then player 2 has to put in another dollar. After player 1 raises, now player 2 doesn't know whether player 1 has a black card or a red card, and so player 2 has the option of either calling player 1's bluff, maybe in this case, or just folding, saying, okay, no, I'm not going to take a chance and I would rather just fold. And so that's the structure of the game. If player 2 calls and player 1 actually has a black card, then player 2 has lost $2 and player 1 has gained $2. If player 2 chooses to fold, then either way, player 1 gains player 2's dollar. If player 2 calls and player 1 has the red card, player 1's bluffing, then player 2 gains $2 and player 1 loses $2. So that's the structure of the game. We can use the tools available to us to actually figure out player 1's best strategy here. And that will involve a little bit of bluffing, but exactly how much would constitute an equilibrium? So that's going to be the objective, and let's see. Let's move on. So I'm going to erase this description and then just write out the strategies, write this game out in strategic form rather than extensive form, and look at the payoffs and try to find the equilibrium. also, once you're done with this, I want you to try out exercise 316.1. The solution's already in that book on Canvas. Exercise 316.1 looks like this. Let's write out the strategies for player 1. Now player 1 has 2 histories, after which it's player 1's turn, and also basically 2 different information sets. And so player 1's strategy would have to specify what player 1 does here, as well as what player 1 does here. So the strategies can be raise, raise, so raising in both cases, raise and C, C and raise, or C and C. For player 2, there's only one information set. Right? If it's player 2's turn to move, then player 1 has raised, but player 2 doesn't know what card player 1 was dealt. Player 2 only has one information, so player 2's choice is only either to call or to fold. Let's put this in a box. Actually, let me see how the book does it. Book has fold first, so I do need this. These are based out of von Neumann-Morgenstern preferences. Let me show you how some of these were calculated, and then you'll be able to figure out how the rest of them were calculated. So for instance, let's look at SS fold, so this box. SS fold means that player 1 chooses to C in either case, and player 2 chooses to fold in either case. Because player 1 chooses to C in either case, it never actually gets to fold, and the outcomes are 1 minus 1 with a 50% chance, and minus 1 1 with a 50% chance, and that averages out to 50% of 1, 50% minus 1, that's a 0, 50% minus 1, 50% of 1, and that's a 0. So that's how these payoffs are calculated for SS. Let's look at another one. Let's see RS call, half and minus half. How did we get that? Player 1 chooses to raise here, C here, and player 2 is always calling. Right? So that means that with a 50% chance, player 1 gets 2, and with a 50% chance, player 1 gets minus 1. 1 minus 1 half is 1 half. With a 50% chance, player 2 gets minus 2, which averages out to minus 1. Basically, 0.5 times minus 2 is minus 1. With a 50% chance, player 2 gets 1. And so that averages out to a negative half. Okay? And so that's how the rest of this table is filled in. I'm not going to go over every single value. So try to go over the other values. I hope this makes sense. If it doesn't, please talk to me in the Zoom meeting. Be happy to go over this again. Okay, so this is the strategic form of this game. So now let's see what the best responses are. If player 2 chooses to fold all the time, then player 1's best response are either to raise all the time, or to see when player 1 has black, and raise when player 1 has red. Remember that black wins and red loses. If player 1 calls all the time, then player 2 calls all the time, then player 1's best response is just to raise when player 1 has black and see otherwise. So definitely don't raise. If you know player 1's going to call and you have a red card, the card that loses, then don't call. Okay. If player 1 always raises, then player 2's best response is to not call. Is to call, rather than fold. Because if player 1 always raises, then player 2 will win at least half the time, and that's better than folding all the time. If player 1 only raises when player 1 has a black card and sees otherwise, then it's better to fold. Right? Because then you'll lose every time player 1 raises, and you're going to win some of the time, but that's really not worth calling all the time. If player 1 sees when player 1 has black and only raises when she has red, then it's better to call. And if player 1 sees all the time, then it doesn't matter what you do as player 2, you're best responding. Weird thing about this is there's no pure strategy Nash equilibrium, right? No two green stars together in the same cell. Also, another thing worth noting is that what's worth noting? A mix of these two strategies is playing both of these with some positive probability. So you get something positive here, something positive here, strictly dominates SS. So you never, as player 1, ever play SS in any equilibrium. Right? It just does not make sense. Also worth noting is that here you get 1 when, if you play raise-raise, you get 1 if player 2 folds. You get 0 if player 2 calls. Here you get 1 if player 2 folds, negative half if player 2 calls. So RR weakly dominates SR, which also means that if player 2, so there's no pure strategy Nash equilibrium, we have to have a mix. If player 2 is mixing and is putting even a slight positive probability on calling, then you'd also never play SR. Which means that as player 1, your only two choices when you're mixing are these two. As player 2, you have these two choices to mix with. And so we use the standard way that we always do to find a mixed strategy Nash equilibrium. Let's say player 1 assigns a probability P to raise and 1 minus P to raise and C. And let's say that player 2 assigns a probability Q to folding and 1 minus Q to calling. In order to allow player 1 to mix between these two strategies, player 2 would have to have a particular mix of Q and 1 minus Q. In order to allow player 2 to have that particular mix, player 1 would have to mix appropriately between choose the appropriate P and 1 minus P, mixing between playing raise or raise C. Note that raise it implies that you're bluffing some of the time. Raise C implies that you're raising when you have good cards, and seeing, so just losing the minimum amount of money you're going to lose, basically. Folding, rather. It's kind of like folding when you have the low type card, the red card. Okay, so if I'm going to keep player 2 indifferent between folding and calling, what sort of P do I have to choose? Player 2 from folding gets a value that's equal to negative P, and the expected value of player 2 from calling is equal to negative 1/2 of 1 minus P, which is equal to negative 1/2 okay, in order to keep these two things equal to each other, I need P equals, so negative P equals negative 1/2 plus P by 2, negative 3P by 2 equals negative 1/2, P equals 1/3. Right, so here P will equal 1/3, 1 minus P will be 2/3. Okay. And we conduct the same exercise for player 2's mixing. So player 2 will be choosing a Q so as to keep player 1 indifferent between playing RR and RS. From playing RR, player 1 gets the expected value player 1 gets from playing RR equals just Q, right? And from playing RS, equals 1 minus Q divided by 2. Because with the probability 1 minus Q, you're in RS call and you get 1/2. So 1/2 minus Q by 2 equals Q, 3Q by 2 equals 1/2, and that means that Q equals 1/3. And that is our mixed strategy Nash equilibrium. So in the mixed strategy Nash equilibrium, player 1 is going to choose RR 1/3 of the time, which means that a sixth of the time, so player 1 is actually going to end up with red and will raise. Alright, so that is the game.